Now that we've reviewed two basic results about prediction in general, we'll turn our attention to the main topic of this lecture: how to predict a count variable. Suppose y is the number of children that a woman has. This is a count in that it could be 0, 1, 2, 3, and so on, but it can't take on fractional values, it can't take on negative values. Say we want to predict y in terms of some observed covariates x, for example, years of schooling, age, whether or not a person is married, and so on. What are the special features of this count data prediction problem, and what does that tell us about how we should go about trying to solve it? We know from the preceding video that the best predictor of y using x in the minimum mean squared error sense is the conditional mean of y given x. In practice, however, this can be quite a difficult object to estimate. So we might content ourselves with the best linear prediction, OLS, and indeed, if the conditional mean function is sort of approximately linear, then this is a reasonable approach. However, if y is a count variable, then it can't be negative. But the OLS prediction, x prime beta, could be. At the very minimum, we would like our predictions to actually be possible values of y, so this is a bit of a drawback. An idea for overcoming this problem might be to work with, say, the logarithm of y. So we might consider a log linear model of the form log of y equals x prime beta plus epsilon. This solves the problem of negative predictions, because it's perfectly fine for the log of y to be negative, so we're simply modeling y on a different scale, where the fact that x prime beta could be a negative number doesn't present any difficulties. However, what if a woman has no children? Y is a count, and counts can be 0, but the log of 0 is minus infinity. So in solving one problem, we've actually created another one. To ensure that our prediction for y is non-negative, we in fact must use a nonlinear model. There's a bit more discussion of this fact in the lecture notes. The approach that we'll take here is to assume that the conditional mean function of y given x follows a parametric form, namely m of x and beta, where m is a known parametric function and beta is an unknown vector of parameters. We'll choose m to ensure that our prediction is always positive regardless of x and beta, and indeed this means that m cannot be linear in beta. In this lecture, we'll focus on a specific example that's extremely common in practice. We will assume that m of x beta is equal to e to the x prime beta, which I also write as exp of x prime beta. This function is strictly positive, and it's very common in practice. Everything I'm going to discuss in this lecture actually works with other choices of m. You just have to make sure to make the minor notational changes where necessary. Throughout this lecture, we will assume that the expected value of y given x is e to the x prime beta naught, where beta naught is the unknown true parameter of the conditional mean function. As you recall from our lecture on minimum mean squared error prediction, that means that beta naught is the solution to the problem of minimizing the expected value of y minus e to the x prime beta quantity squared over all possible parameter values beta. So, how might we go about trying to estimate beta? Well, one idea is to use the so-called nonlinear least squares estimator. This is defined as the minimizer of the sum from I equals 1 to n of yi minus e to the x prime beta quantity squared. This is effectively the sample analog of the mean squared error from above. There's nothing wrong with the nonlinear least squares idea, but in practice it's much more common to use Poisson regression to solve this problem, for a reason that we'll discuss at the very end of this sequence of videos. In Poisson regression, we posit a model of the form yi given xi is a draw from a Poisson distribution with mean equal to e to the x prime beta naught, with a series of independent observations, we have a maximum likelihood model, and we will set about to estimate beta naught, the unknown parameter vector. This may look somewhat similar to the examples that we saw in our first lecture, but there is an important difference. This is not a model for y unconditionally, nor is it a model for y and x jointly. It's a model for y conditional on x. So before we can understand how it works and what the properties of an estimator constructed from it might be, we need to take a bit of a detour to consider the problem of so-called conditional maximum likelihood estimation. And to do this, we will expand upon some of the ideas that we studied in Lecture 1 about the behavior of maximum likelihood estimation under misspecification and the associated asymptotic properties.